All right, we just spent some time in Chapter 2 looking at sections 2.4 and 2.5 and dealing with how to solve right triangles. And those were easily solved with just trig relationships using um, the sine is equal to opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent being opposite over adjacent. Now we're going to look and see what's happening with just any old triangle. So any old triangle we call an oblique triangle. There's no special angle in there. And what we can do is take a look at using either what we call the law of sines or the law of cosines in order to help this out. But in order to use those, they're applied in very specific settings. We would love to use the law of sines first, and that's what's taught first, and then use the law of cosines. So if we start with what they call the congruence axioms, these are the things that we're looking for. Um, you're not going to be able to solve any old triangle without some pieces of information. And so one of the pieces of information we could have is a side, angle, side. So if two sides and the included angle of one triangle are equal um, respectively, or two sides of the included angle of a second triangle, then the triangles are congruent, right? So if you have a side, angle, side, then the two essentially side angle side when we say that. Now they're talking about two triangles being congruent to one another. And so side, angle, side. So you'd have to know two sides in the included angle. So it could look like that, could look like this, or it could look like this, right? But all of those are side, angle, side. Okay, so just to give you an idea of what that is, the next one is angle, side, angle. So if you think about angle, side, angle, um, um, that would be if two angles and the included side of one triangle are equal respectively to two angles and the included side of the second triangle, then the triangles are congruent, relatively equal to one another, right? And so they're using congruent as opposed to similar triangles like we had before. So what is angle, side, angle? Well, you'd know two angles of a triangle and an included side. Um, and so what I want to remind you of is if you know two angles, then you absolutely know the third angle as well. And so it's not enough, though, just to know two angles of a triangle. You got to know that third piece of information, and um, it's gonna make a difference which angles we know. So angle, side, angle would include that. The side that we know is included in between those two angles. And then we could know the three sides, right? No angles, but if you know the three sides, then the triangles are congruent as well. What we do know, though, is if the three angles are equal, then they're similar triangles, but we don't know about the relationships. We can't say that they're directly equal. So whatever we have side, or angle, or side, side, the triangle is unique, meaning we can solve for it. An oblique triangle is a triangle that is not a right triangle. That's what I was trying to say in the beginning. Information sufficient to solve the triangle, you absolutely need to know at least one side and any two other measures. So if you go back up to each one of these cases, the congruence axioms above, uh, which is really from geometry, and they're just pulling that out. Every single one of them we know a side, and then two other pieces of information. So as long as you have that, you'll be able to solve the triangle uniquely. And so here's what happens. The data required for solving a triangle, right? So before, with the right triangle, I needed to know like two sides or a couple of angles or something like that. Here I got to know a little bit more. And so the data required for solving an oblique triangle, side angle angle or angle side angle. So notice we didn't do side angle angle up here. So if you know two angles and a side, or if you know, well, actually that's it. If you know two angles and a side, guaranteed to be able to solve the triangle uniquely by using what we call the law of sines. And that's going to be presented in this section and then the following. If you know two sides and one angle not included between, this may lead to more than one triangle. Okay, so if you know two sides and not the included angle, then you can use the law of sines, but it could lead to more than one triangle. That's 7.2, right? This is 7.1, and that's what we'll see in this area today as we talk. And then if you have two sides and the included angle in between them, we are going to be able to use the law of cosines, and three sides, you're going to be able to use the law of cosines. So before you get crazy, like, I got to remember all of that, it'll be really natural. So here's what you want to know. So just taking a little Jensen aside, if you know the side, actually, let me change that to a side. If you know a side, and then I'm also going to change this to be a different color, and the angle opposite it, you use the law of sines. Okay, and if you don't, then you use the law of cosines. So again, you have to be given a side and two other pieces of information. You can solve a triangle. So let me just show you what I mean by that. Let's look at side. Let me go from case 1 and look at side, angle, angle. So if you got side, angle, angle, here's the side, here's the two angles. You definitely know the side and the angle opposite. Law of sines is going to unlock everything. If you look at angle, side, angle, then what that looks like is angle, side, angle. Now you're saying, well, I don't know if here's the given side that I know, and I'm not given the angle opposite it. However, you can figure it out. What do the three angles of a triangle have to add up to be? They have to add up to be 180. So you can easily figure this out by 180 minus angle 1 minus angle 2. So you'll know the side and the angle opposite. It doesn't have to be flat out given to you. You can do a little bit of work to solve it. So if I leave this section, I'm thinking, okay, if I ever know two angles, and I always have to know a side, right? They're not going to give me anything other. We're not going to be able to solve anything if I don't know a side. So if you know a side and any two other angles, you know everything. You're going to use the law of sines. You'll know all the angles. So if those other two pieces of information are both angles, it's the law of sines. Let's take a look at side-side angle. If I'm given side-side angle, what's that look like? Side-side angle. Notice I know an angle and the side opposite it. Now what they're saying with this situation is it could lead to more than one triangle. Okay, two triangles could solve that thing. They call this the ambiguous case of the law of sines. And actually, sometimes we get no triangle being able to solve it, depending upon no triangle being able to be that way. But if you look at the other one, so notice the other one, where we go to case 3, is side, angle, side. What's that look like? Well, that's side, angle, side. There's going to be no way for us to know what either of these angles are, right? Here's a given side right here, but I don't know the angle opposite. Here's another given side, but I don't know it. And there's lots of possibilities for these two. So we're going to have to use the law of sines. Law of cosines. It's because I don't know a side and the angle opposite it. So there are ways, and here I don't know the angle any of the angles, so I got to use the law of cosines. And it's not like the law of cosines is bad, it's just a little bit more involved than the law of sines. So let me end this video here where we do a brief introduction to when to use the law of sines and when to use the law of cosines. That way the video doesn't get very long. And then what we're going to do is we're going to develop the law of sines and then use it in the following video, still here in 7.1.